introduction. Let me share my screen. Just let me know my screen is visible.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Just wait, just wait, just wait. Okay. Good afternoon, everyone. I hope I am audible to all. Good afternoon, everyone. I hope I am audible to all.
Yes, ma'am. Yes, ma'am.
Okay. So first of all, I would like to thank the organizers of this STTP short-term training program for inviting me to deliver this expert lecture. So already she introduced my name. So today we are going to discuss one of the most exciting development in artificial intelligence. Just wait. So, okay. Okay. So the title of my talk is From Data-Driven AI to Physics-Guided Intelligence. The evolution of future computing methods. Right. So nowadays, what happened that almost everyone uses AI, that is artificial intelligence. We use, hopefully we all of use right now that ChatGPT, or we can use Google Translate, or we use image generation tools. So we use recommendation system on YouTube, Netflix. So many people, what happened that think that AI can solve any problem. But can AI solve engineering problems? Can AI solve fluid flow or heat transfer? Or what I can say that the structural mechanics, or the climate prediction? Okay, so obviously the answer is not always. AI cannot always solve all these type of problems. So this is because the scientific and engineering problems are very different from language or image problems. So scientific problems allows, so all the scientific problems, what I can say that scientific problems having the mathematical equation, right? So they follow the laws of physics. Now, just one question. My screen visible? I changed the slide. Okay, thank you. So in this slide, what we can say that we begin a simple question. Okay, so please look into this figure. Okay, one on the left side, we can see that the applications where AI performs extremely well. For example, we are using ChatGPT. We know that their AI perform very well. Image recognition, or autonomous driving, or deep learning. So these systems learn from huge amounts of data. It requires huge amount of data. Now look in the right-hand side, right? Right-hand side of this slide. Okay, so what happened? What we can see, the right-hand side, that we can see that the fluid flow, the heat transfer, the climate modeling, Okay, the engineering simulation. So these problems are much more difficult, much more difficult. Why? Because these systems are controlled by the physical laws. For example, water flowing through a pipe follows the Navier-Stokes equation. We, from mathematical background people, they can know this equation. Okay, so heat transfer follow the heat equation. Electromagnetic waves follows the Maxwell equation. So this equation cannot be ignored in real life problem, right? So let me ask you one question. Suppose ChatGPT read millions of books, right? So can it suddenly predict how the water flows around an aircraft wing? So answer is obviously not always or no, right? So because the language data alone cannot teach physics. Similarly, if we are considering an image recognition model that cannot directly solve our differential equation. Okay, so the difference motivates, these different motivates actually the today's topics. Okay, so traditional AI learn from data, scientific computing learn from physics, and future AI should learn from both, obviously, right? So this is exactly where physics informed neural network, that is PINN works, come into this picture. So today's lecture is about combining the strength of artificial intelligence with the strength of mathematics and as well as physics. Okay, so before discussing AI, let us first understand how computers solve problems before artificial intelligence exists. Okay, so in that time, what happened? In that time, let us go back for several decades. And before machine learning, before deep learning, even before ChatGPT, computers were simply machines that follows the instruction. What happened? A computer never thinks, never understands, and it simply executes the instruction given by the programmer. We all know that thing. Okay, so the process is simple. Input comes to the computer and the program process this input, the given input, and the computer produce the output. So everything depends on the program, right? So if the programmer writes correct instruction, the computer gives the correct results. So if the programmer make mistake, then what is the computer also make mistake. So there is a old saying. You can all of you may know that thing. That is garbage in and garbage out. What do you mean by that? That is bad instruction produce express bad results, right? So the traditional computers never learn from the experience. Okay, so if they solve one problem today, they do not become smarter tomorrow for the traditional system, right? So every new situation requires new programming. Okay, so so now think about this, that suppose we write a program, we to recognize the handwritten digits, right? So what happened? Can you write the rules for every person's handwriting? So is it possible? So it is an impossible task, right? So there are millions of handwriting styles. So this millions, so for this millions of handwriting styles needs millions of inputs, instructions. So it is actually impossible task for us. So so the limitation, this is obviously the limitation. So the limitation motivates researchers to ask a new question. What is that? That instead of program for every rule, can the computer learn this rule by itself? The simple question changed the history of computing actually. Okay, so this idea brings to us the traditional way of computing. Now, the traditional way of computing, as we are saying, that traditional traditional computing follows a very simple process. What of that? That is input, programming, and then output. So everything depends on the program written by human experts, right? So the programming already knows the solution, right? Obviously, because everything instruction is given. So as per the instruction, the output will arise, right? So the computers simply follow the instruction. Now, what happened? Traditional computing works very well for structured problems. So like banking software, if we are saying that payroll systems, or we can say that normal calculations or tax calculation for that thing. Okay, so this system have clear rules. They rarely change, right? So traditional computing is reliable. It is accurate and it is easy to verify, right? So this is why we can say that it has been the foundation of the modern digital systems. Okay, so let's see both the strengths and weakness of the traditional systems. Okay, so every technology has advantage as well as its limitation, right? So traditional programming is no exception, right? So let us first discuss the strength. So you can see from the slide already, it is displayed that it produces the predictable results. If we give the same input, we always get the same output. But whenever you are using ChatGPT or something for the modern computing programming computing, in that case, you can check it out. Never. Each and every time you will get the similar type of result, but they are different, right? So as we are saying that for traditional programming, it is always giving the same results, right? It is highly reliable, it is mathematically accurate, or it is easy to test and verify. Okay, that is why the banks and space missions or whatever the things are, they are using the traditional programming. Okay, so now let us discuss its limitation. The biggest problem is that the human must write every rule. Okay, so without the writing the instruction or the rules, they can perform well or perform the whatever the requirement. They cannot reply on that. Okay, so imagining writing tools for recognizing millions of faces, so it is impossible, right? So another problem is complexity. Okay, as the problem become larger, the number of rules grows rapidly, right? So managing thousands or millions of rules become extremely difficult. So traditional programs also cannot learn, right? So if no situation or new situation appear, then what happened? The programmer must update the software again. And therefore, the traditional programming is excellent for simple and well-defined problem, but it struggles with complex and real-world application. So one famous example clearly show this limitation. So you already know this thing. What is the thing? The thing is that the examples of chess as a computing challenge. Okay, so many years ago, researcher wanted that a computer to play chess. Right. So initially they tried the traditional programming. Expert wrote thousands of chesses rules, and they encoded opening moves, middle game strategies, and end game techniques. Right. So the computer follow these rules, but what's the problem? What is that? Right. So the problem is the chess has an enormous number of possible moves, right? Because you already know that how the there, right? So no human can write rule for every situation. Eventually, researchers changed their approach. Instead of programming every rules, they allowed computer to learn from millions of chess games, right? So the computer started identifying the patterns. It learned the moves by experience, or we can say that this is revolutionary changes, right? So this computer was no longer simply following the rules. Okay, so it was learning. And today, AI systems such as you can say that AlphaZero launches by playing against themselves. So no human programmed millions of rules. The system discovered many strategies automatically. And what we can say that this example beautifully demonstrates that the transition from programming to learning. Okay. Next, we can consider as a technology advance, the world generated enormous amounts of information, right? So problems also became much more complicated. Many real world problems having no fixed mathematical rules. For example, for speech recognition, if we are considering, or if we are considering the medical diagnosis or traffic prediction, anything. Okay, so writing rules for these problems become impossible. At the same time, what happened? The computer become faster, storage becomes cheaper, and the internet generated huge amount of data. Researcher realized that something important, obviously. So data itself contains hidden knowledge. And what is that? Instead of writing rules, why not allow computer to learn the patterns directly from the given data set, right? So this is a simple idea created a completely new computing paradigm, right? So the focus shifted from the writing programs to learning from the given data set. So data become the fuel of the artificial intelligence. Now, why did data become so important? Okay. So today we generate data almost every second. All of you know that. Okay. Every Google search create data. We can say that every WhatsApp message creates data, or we can say that every online purchase nowadays we are doing mostly. Okay, so online purchase create data. Okay, smartwatch sensor create data, satellites produce data. So factories generate data, hospital generate data. So lot of data. So data are everywhere actually. And of course, in laboratory and the scientists generate the experiential data, experimental data, right? So yeah, and even social media platform later generate. We already know that Twitters are there, Facebooks are there, YouTubes are there. Generate billions of trillions of records every day. Right. So this enormous amount of information become a valuable resource. So people often say data is new oil. Okay, data is new oil, but I like to say that data is the new fuel for the AI. Right. So without data, machine learning cannot learn, and without data, deep learning cannot improve. So large data set allows AI system to discover what we can say the hidden relationship. However, collecting a good quality of data is still a major challenge. We already know that those who are working with the data set, to get a good quality of data is very tough nowadays, right? So we will sure discuss it later. Okay, so now data to intelligence, right? So how? The people think that data and intelligence are the same, but actually they are very different. Let us understand this step by step. First stage is data. Data is simply raw facts. Okay. The second stage is information. When data is recognized, it becomes information. Third stage is knowledge. The knowledge identifies useful pattern, right? And fourth stage is intelligence. Intelligence uses knowledge for decision making. And finally coming learning, the final one. Okay, so learning allow computer to improve automatically from experience, right? So this is exactly what machine learning does. So machine learning transforms raw data into a predictive models, right? So this is why the data is the starting point, but intelligence is the final goal. Now, the term big data is often explained using the 5 V's. What are that? The first one is volume. This means the amount of data, how many data are there in the given data set, right? The second one is velocity. What is that? The data is generated continuously. Like, for example, what we can get, stock market, social media, already discussed earlier, right? Third one is variety. What is that? Data is not only the number. It includes text, it includes sometimes images, it includes videos, it includes audios, medical reports, satellite images, etc., etc., etc. The fourth one is the variety. This refers to data quality. What do you mean by that? Data quality? Data quality is suppose, or is the data is accurate, or it is complete data? Can you trust this data? Something like that. And the fifth one, the final one, is value. Collecting data has no benefit. The real goal is to extract useful knowledge. Good data help us to make better decision, right? So predict future events and solve complex problems. So these 5 characteristics explain why big data has become the foundation of modern artificial intelligence. As I am saying that data is everywhere. Okay, so we know that data is important. So next question is, where does all this data come from? Okay, so we already discussed this thing, right? So from where we can getting this data, like a smartphone, like social media, like hospitals, like satellite, like stock markets. So from everything. Okay, so so this one is the programming from the writing, right? Very important. That is, it shows that one of the biggest changes in history of computing. What is that? Look at the upper figure. Okay, what is meaning of this figure? This is the traditional program computing, right? So this process is simple. We already discussed traditional computing. Okay, so it provides, we provide input and programmer write the program and computer produce output. So everything depend on the human written rules. Okay, and now look in the lower figure. So what is this? This is machine learning. Okay, so what we can do there? So here we provide data instead of rules. In traditional, we are providing instruction in the programming, right? So here we are not providing any instruction. Okay. So the learning algorithm studies this data because we are providing the data set. So it is automatically built a mathematical model. And finally, the model makes the prediction on new data. So this is completely a different approach. So instead of what we can say that teaching the computer every rule, we allow the computer to discover the rule by itself. Okay, so the machine learning algorithm automatically learn the difference. So this is why machine learning is called learning from examples instead of programming with the rule. Okay. Now, very important question. So many people believe that more data always give better result. That is partly true, but generally, larger data set improve learning performance. However, these are many situations where the collecting data is very difficult. We know that, right? So how Think about the prediction of earthquake to predicting earthquake. Okay, so can we generate thousands of earthquake for test training? No, it's not possible. Of course not. Okay, so consider the rare disease. Hospital may have only few patients records, or sometime more. So all these things are where we cannot collect the large amount of records or the data. Okay, so similarly, scientific experiments may take months or year, whatever we are doing in the laboratory, right? So another challenge is what we can say, that data quality. Sometimes data contains error, we already know that, and sometimes measurements are noisy, it may be possible, or sometimes important informations are missing, it may be found in the data set. So simply collecting more data is not always possible. So this creates important research question. Out of that question, that can machine learn efficiently even when what we can say that only few amount of data are available. Okay, so yes, very important question. So this question actually eventually lead the researcher towards the physics informed machine learning. But before reaching that stage, first we need to understand machine learning itself. Okay, so what is machine learning? Machine learning is one of the most important branches of artificial intelligence. We already know this thing, right? So instead of following fixed rule, machine learning learn from data. The main objective is very simple: learn pattern from the past examples, right? So then those patterns to predict the future outcome. So let me explain with a simple example. Suppose we have data about the house prices, right? So for every house, we know the area of that house, the number of bedroom exist, the exact location, and the selling price, etc., etc., etc. So many parameters are there. Now, the machine learning algorithm studies these examples. Then a new house appears, it predicts its price. So notice something important. Nobody programmed the exact pricing formula in this case. So computer learned it automatically, and machine learning improve with experience. So more good quality of data it receives, the better it usually performs. So that is why the machine learning has become the foundation of modern artificial intelligence. Now, the limitation, obviously, the limitations are there. Our traditional programming worked well for many years, but the modern problem becomes too complicated. So just if we are considering that many real world problems are too complex. For example, if we are recognizing human emotions, or driving autonomous vehicles, or we can say that understanding the natural language, or the writing rules for every situation if it's possible, right? Secondly, human expert cannot predict every possible scenario. It is not possible. Okay. So third one is data become easily available right now, nowadays, right? Fourth one, computer become much faster, right, nowadays, because powerful processors we have, and the GPU made machine learning practical. And finally, the industries needed intelligent system that could improve automatically. So machine learning solved this problem. So instead of depending completely on programmers, it allowed computer to learn directly from experience. Now, machine learning workflow. So building machine learning model is not just about selecting an algorithm, right? So in the back end, there is so many steps are there, right? So it follows a complete workflow. So the first step, what is that? First is defining problem. We should clearly know that what we want to predict. Then need the data collection, right? Without good data, no model can perform well. The third step is data preprocessing. Here we remove the missing values or the correct errors or normalize the data. The fourth is feature engineering. So for the feature are the important characteristics for the data, right? And then model training. The algorithm learns relationship from the training data. And after training, we evaluate the model. We check the accuracy, we compare the prediction with the actual values. And finally, we deploy the model for real world applications. So only after successful testing do we use it for market prediction. And machine learning is a systematic process. So no, not simply running one algorithm. Okay, so under that there are various type of algorithm of machine learning exist. Okay, so what are that? Various type of algorithm, as we are saying that supervised learning, first one. Okay, so we already know that the correct answer in this case, supervised learning. The algorithm learns from the label example. Okay, second one is unsupervised learning. Here, the label are not available. So the computer tries to discover hidden pattern by itself, right? And the third one is reinforcement learning. Okay, so this is similar to learning by trial and error. So the computer receive rewards for good decision and it receive penalties, right, for wrong decision. So supervised learning is most commonly used in engineering applications. Next, unsupervised learning. Unlike supervised learning, unsupervised learning does not use label data. The computer received only the input data. It tried to identify the hidden pattern automatically. So one common task is clustering. We can do cluster groups, what I can say, similar like of data together. Okay, and another important task is dimensionality reduction. What is that? Sometimes it may be possible that hundreds of parameters of the data exist to take all that 100 parameters work for. Okay, so sometimes we have to reduce the dimension. We have to choose that what are the important parameter, and we are working with that. Okay, so so unsupervised learning is widely used. We can say that in customer segmentation, anomaly detection, fraud detection, or we can say that market analysis, data visualization. Okay, so although it is more challenging, it is extremely useful when labeled data are unavailable. So we already know that there are several type of machine learning algorithms are there, right? So each algorithm has its own strengths. Okay. First is say regression. If we are saying the regression model, it predict the continuous values. When we are applying the regression model to the given data set, when we are getting the continuous value in the data set, right? Next is decision tree. It makes the decision step by step, just like what I can say that answering a series of yes or no type of question. Okay. Another important algorithm is SVM, that is support vector machine. Okay, so it first the best boundary between, find the best boundary between what I can say that different classes, right? And it works well for classification type of problems. Okay. Next is KNN, that is nearest neighbor. So it predicts based on the similar examples. So it follows a very simple ideas. Similar object usually have similar properties. Okay, and finally we have the ensemble method like random forest and gradient boosting. Okay, so instead of using one model, they combine many models. This often produce better accuracy, right? So there is no single best algorithm, we can say. So the choice depending on the given problem, the data, the computational resources, etc., etc. So machine learning has solved many real problems. However, it is also some limitation. So those limitations eventually lead the researcher to develop deep learning. As we today's talk, we are going through the traditional computing to machine learning to deep learning to scientific computing to physics in for neural network. Okay. So far, we learn about machine learning and it is how it is work, right? So now, one question. Has machine learning solved every problem? We already know the answer. What is the answer? The answer is no. It's not possible. Okay, so machine learning has achieved remarkable success in many fields. We already know that. Okay. For example, for example, if filters of spam emails, right? So it recommends also the movies from the Netflix. Okay, so it suggests products from Amazon, right? But machine learning also have some limitation. What are that? That one major limitation, I can say that feature engineering. Now the next question is, what is feature engineering? It means that a human expert must decide which input features are important. Another limitation is the traditional machine learning struggles with high dimensional data. For example, images, videos, speech, natural languages. So in that case, the data are very high dimensional because lots of parameters exist. Right. So if you imagine recognition a human face, so a single image contain million should automatically learn the features themselves, right? And this idea give the birth of deep learning, we can say. So the next is why deep learning change artificial intelligence. So around the year 2012, artificial intelligence experienced a major revolution. What is this? This evolution is called deep learning. But why it is so successful? Traditional machine learning required human experts to design the features, but deep learning removed this requirement. So it automatically learns from feature directly from the raw data. And suppose we want to recognize chat in images. Earlier, expert tried to identify the features like ears, eyes, wrinkles, tails, etc., etc. Right? But deep learning does not need this manually designed features. It learns everything automatically. And another reason for its success is available of large data set. Today, billions of images and videos are available on the internet. And deep learning has also become possible because the power of GPUs. GPU can perform millions of calculations simultaneously, and deep learning was also inspired by the human brain. Although it is much simpler than the brain, obviously, so it follows similar idea of read, interconnected neurons, because these advantages, deep learning achieved record-breaking performance in computer vision, speech recognition, or language translation, and many other applications. So this is why today's AI systems are mostly based on deep learning. The foundation of deep learning is artificial neural network, or ANN. We can say this thing. The idea becomes from the human brain. Our brain contains billions of neurons. These neurons communicate with each other, right? And artificial neural network try to imitate this process in a simplified way. Each artificial neuron received the several input values, and every input has associated with an weight. The weight represents the importance of the given input, and the neuron multiplies each input with that weight. Then it adds all the weighted inputs together. A bias value is also added, right? And finally, the results passes through an activation function. The activation function decided whether the neuron should produce a strong or weak output. So this output becomes the input of the next layer. This process continues until the final prediction is generated. Okay. So this is the work procedure of this one. So the architecture, what is the architecture of this one? So neural network is organized into different layers. So the first layer is called the input layer. It receives the input data. Second part consists one or more hidden layer. Okay, so this layer perform most of the learning, and they identify the patterns, and they combine the informations. They gradually understand more complex features. And finally, we have the output layer. It produces the final prediction. Now, the question is, why deep learning? The traditional neural network contain only one or two hidden layers. These are called shallow network, actually. So they can learn simple relationship. However, the real world problems are much more complicated. So deep networks contain many hidden layers. Each layer learn increasingly complex information. Let us consider image recognition. The first layer detect the images, second layer detect the simple shapes, the third layer combine the shapes into the objects, and the higher layer recognize the object like car, humans, or animal, etc. So deep learning eliminates the manual feature engineering. So instead of asking experiment to design feature, the network learn useful feature by itself. So this is one of the biggest reason behind this success. So this how does neural network learn? So we already say this thing in the previous slide, that is it learned by step by step. The first we provide input data, so we already discussed this thing. Okay, now this is very important: back propagation and optimization. Back propagation is the heart of deep learning. It is the algorithm that teaches the neural network, and the learning process has several steps. First, the network makes prediction. Second, calculate the prediction error, and third, the error is sent backward through the network, and this is called backpropagation. And during this backward movement, the network update the weight of the every neuron, right? And these updates are performed using an optimization algorithm called gradient descent. And gradient descent simply moves the weights in the direction that reduces the error. So this process is repeated many times, and each complete pass through the training data is called epoch, right? And with every epoch, the network learn a little better. Eventually, the loss become very, very small, and the prediction become accurate, to more accurate, right? So this is how the deep learning model improve continuously. So this is deep learning architecture. The simplest one is many types of neural network. Each one designed the specific type of problem, and this simplest one is the feed forward neural network, or we can say that FNN. And then the next comes CNN, that is convolutional neural network, and then the third architecture is RNN. Achha, one more thing for CNN. CNN are widely used when the medical image analysis or satellite image processing or self-driving car. In that case, we are using that one. And for RNN, are designed for the sequential data. Okay, so for example, stock price, weather prediction, time series forecasting, etc., etc. So, however, RNN struggle the long sequence, and the overcome this limitation, researcher developed LSTM. What is LSTM? LSTM is long short-term memory. Why this is required? Because LSTM remember the important information for a longer time, right? And short-term memory, যেগুলো লাগবে না, মানে those who are not important, they forget. Okay, for this is used in speech recognition, language translation, and financial forecasting, etc. So each architecture is designed to solve the particular class of problems. Next, transformer and foundation model. So one of the biggest revolution in AI happened in the year 2017. A researcher introduced the transformer architecture. Unlike the previous network, transformer process entire sentences simultaneously. They use mechanism called attention, and attention help the model focus on the most important words. The transformer understand all that things and solve the problem very efficiently. And today, transformer are the foundation of AI, of modern AI, we can say that, because ChatGPT, Google Gemini, Cloud, and many other LLM, that is large language model, all are based on the transformer architectures. Now, applications of deep learning. Deep learning is now part of our everyday life. So many people use it without realizing it, right? So computer vision helps to recognize faces, detect objects, analyze medical images, natural language processing power, ChatGPT, machine translation, or intelligence chatbots. Similarly, speech recognition convert spoken language into text, like Google Assistant, Siri, or Alexa we are using, right? Autonomous vehicle use deep learning to identify roads, traffic signs, etc. Healthcare uses deep learning to detect the disease from X-rays or CT scans or MRI images, right? Similarly, drug discovery has made much faster because AI can analyze millions of chemical compounds. Robots use deep learning for navigation and object recognition. Bank use it for fraud detection and financial forecasting. Similarly, scientists use deep learning to analyze climate data, satellite images, biomedical images, information, etc. So deep learning has transformed almost every every field. Okay, so however, despite of this amazing achievement, what I can say, deep learning still have important limitation, and it require a huge amount of label data, and it is often called black box. Okay, and most importantly, it does not automatically understand the law of physics. So this limitation become the critical in scientific and engineering problems. And this is exactly where the next part of our lectures begins. So next is challenges. Challenges of purely data-driven AI. So far, we already discussed the remarkable achievement of deep learning. So now let us ask one question. Is deep learning perfect? So what is your answer? Obviously, no, it is not perfect. So deep learning has many strengths. Many strengths. It can automatically learn feature, recognize image, understand speech, generate text, anything it can do. However, it has some limitation. The first limitation, as we are saying, that it needs huge amount of label data, and collecting such data is very expensive. Sometimes it is impossible also. Second limitation is computational cost. So training a very large neural network requires powerful GPU, and we know that the cost of that. Training may take days or even weeks or even months. Another is interpretability. So many deep learning models are called black boxes. They produce predictions, but they cannot clearly explain why they made those predictions. And this become a series of issues in medicine and engineering. So finally, deep learning learns from the data. It does not automatically know the Newton's law, or it does not know the thermodynamics, or it does not know Maxwell equation, Navier-Stokes equation. So unless we explicitly provide the knowledge of this, the model may produce physically impossible results sometimes. Because whenever you are using ChatGPT nowadays, students are using many times this thing, and you can check the ChatGPT shows or whatever, the Gemini or anything that shows some impossible results. That is why. This is the reason behind it. Okay. So yes, obviously, deep learning is not enough. Though it has changed the artificial intelligence, there is no doubt about that. But today we know it powers ChatGPT, it powers Gemini, autonomous vehicles, medical medicine. But let us think about the scientific problem, and for that there is limitation. Okay, so the experiments are where, if we are considering the experimental data set. Okay, for experimental data set, what we can say, the experimental data set experiments are sometimes it may be possible that they are very expensive. Sometimes some of the experiments may be possible that a very dangerous type of experiment. Sometimes they cannot even be performed. It may be possible, right? And it may be possible that suppose if we are considering one example, so consider earthquake prediction. Okay, so can you generate thousands of earthquake of training? No, it's not possible. Okay, so sometimes the data are not available or easy available. So deep learning performed very well when data are abundant, but and also it requires the label data, as we are saying. Limitation of pure deep learning. Okay, so this slide summarize actually the major limitation of deep learning. We already say in the previous slide. Okay, so I'm skipping this slide. Next, when science challenges AI. Now, the scientific systems are very important, from language to image problem. Nature law follows what we can say that fixed physical laws. right? If we are considering fluid flow, then it follow the Navier-Stokes equation. Heat condition follow heat equation. Electromagnetic field follow the Maxwell equation, and so on. So this equation cannot be ignored. We cannot ignore that thing. Scientific experiments often produce only small number of observations. So measurements may contain knowledge. Sensor may have errors. It may be possible. Sometimes some important variables cannot be measured directly. Okay, so another issue is computational cost. And finally, the scientific prediction must satisfy the conservation laws. So these are some examples of scientific computing problem, like as we are discussing, wave propagation, fluid dynamics, heat conduction, electromagnetic field, structural deformation, ground water flows, etc., etc. Now, as we can say that the data bottleneck is scientific. Why data is more difficult? One of the biggest challenge, I can say that in scientific AI called bottleneck, data bottleneck. What is that? Why is collecting scientific data difficult? First, the physical experiments are expensive. We already discussed. Building laboratory setup may cost millions of rupees or dollars. Secondly, we can say that many experiments require specialized equipments. Third, some experiments are dangerous. Sometimes it may be. Think about the, what I can say, that nuclear explosion, volcanic eruptions, right? So obviously we cannot repeat this experiment many times. Okay, and finally, rare events generate only few observations. So it is obvious. So why should AI learn physics again? So scientists have spent hundreds of years discovering the laws of nature. Like Newton developed laws of motion, Fourier developed the heat equation, Maxwell developed electromagnetic theory, etc., etc. So this mathematical equation already contain valuable scientific knowledge. Okay. So if we can say that the boundary condition, sometimes the boundary condition describe how the system interacts with the surrounding. Initial condition in the differential equation describe the starting stage. The conservation laws ensure the physically correct behavior. So obviously all this knowledge already exists. Instead of resolving or rediscovering from the data, so it should directly use it during learning. So the idea, this is the idea, forms from the physics guided intelligence. Now we move to the depth of our talk, that is data versus physics. So this table actually compares two different approaches. The final approach is data-driven, and the second one is physics-based modeling. So data-driven AI directly from the observation, where physics learn from the mathematical equation. Deep learning requires large data sets, where physics-based model requires scientific knowledge only. Deep learning performs very well for interpolations type of problem, where and physics informed model often perform better to predicting the new situation outside the training data. So another important difference is the physical consistency. Deep learning may have violate physical laws, and physics-based models naturally satisfy them. So finally, the physics-based model are easier to interpret. So their equation clearly explain when the prediction occurs. So each approach has strengths, each has weakness. So best solution is what to do? No choosing one over the other. So best solution is coming from using both the method. Okay, so next main topic, as we are saying, that physics guided intelligence. So The idea is surprisingly very simple. Instead of learning from the data, AI should learn from both the data and physics guided learning needs. Because in traditional, we already discussing at the very beginning of my talk that what is the traditional calculation, traditional computing method, and what we are doing in machine learning or deep learning computing method. Okay, on that method. So one is traditional, another is related with data. Right. So in this case, what happened? Physics guided intelligence. So what happened? We are using both the physics and the data, both. Okay. So what I can say that one most successful methods by using both the physics and with the characteristics of data, it develops in the field that is called the physics informed neural network, or it is called the PINN. This is the main topic of the second half for today's lecture. Okay, so physics based modeling. So now if we are saying that before artificial intelligence become popular, scientists solve engineering problem using mathematical models. Every begins with a physical system, right? I'm not taking the example. You already know fluid flow, heat transfer, etc., etc. So next step is writing the governing equation. You have to write, because whenever the physics concerned, so you have to write down, or mathematical modeling concerned, so you have to write down the governing equation. So this equation, and in generally which type of equation, governing equation, you know already that it's sometimes ODE, it's sometimes PD. I mean ordinary differential equation or partially differential equation. Okay, so if the problem is so it's depending on the given model. If the problem is more simple, then ODE is there. If the system is too much complex, then the PD equations are there. Unfortunately, for real engineering problem are much complicated. So analytical solution do not exist because we cannot find out the closed type of solution. For that reason, we have to use the both. Okay, so for decades, the physics-based numerical modeling has been the foundation of the scientific computing. So it produces a very high accurate result. However, it also has several different disadvantages, I can say. Okay, so it required a mesh generation, I can say, and it is the computational process that is also expensive. So large simulation may take hours, even for days also. So this is the limitation for I can say that to motivate the researcher to combine the numerical methods with artificial intelligence, and that combination of numerical methods and the artificial intelligence is eventually lead to PIN. So this is the workflow for scientific computing. We have to understand how scientists traditionally solve this problem. So we already discussed this thing. I will go for the next slide. Numerical methods. So what methods we are actually using? The methods are finite difference method that approximate the derivatives using a difference equation. And another method is finite element method that divides the domain into the small elements, and another is FVM, that is final volume method. So instead of solving the equation at a point, FVM conserved the physical quantities instead of small controls volume. Okay, so there are very examples are there. I'm not going into deep on that. These are the strength and limitation of physical based modeling, because you can see that based on established the physical law, this this is obviously the strength. This is highly interpretable. This is physically consistent solution and a high numerical accuracy, obviously, and this is reliable for the engineering analysis. And for this one, it is computationally expensive. The mesh generation can be difficult because obviously sometimes it is very, very difficult. A long simulation take times, long times, and perform means decreases for the high dimensional program. So this is the actually the differences in data-driven AI and physical-based modeling, where we can see that data-driven AI is learned from data, and physics-based modeling is based on the governing equation, and this is the first interface after the training for data-driven AI, and it is computationally expensive. And this for data-driven AI, it required large data set, but in this case, we require the physical knowledge, the physics behind it, and so on. Okay. Next, the evaluation of AI. The very important for this one. So if we are in this slide, actually, it represents one of the most important ideas in today's lecture. Actually, the neural network are excellent function for approximator, right? And it can learn highly complex relationship. At the same time, the physics that provides reliable scientific knowledge. So researcher asks a simple question. Instead of learning only from the data, why not also learn from the governing equation, right? The answer is physics neural network. A neural network, that is PINN. Okay, so in this approach, what happened? The neural network is trained using two kind of information. The first is the observational data, and the second one is the governing physical equation. As I am saying, we are saying discussed earlier that data and the background physics both working in physics informed neural network. Okay, so the equation become the part of the learning process, and this achieved by the modifying the loss function. So whenever the network violates the governing whenever the network violates the governing equation, add an additional penalty is added. As a result, the model automatically learn physically consistent solution. So this is simple but powerful idea, bridges artificial intelligence to scientific programming. Okay, so next we need to understand what is physics informed neural network. So this is introduced by Reisi. PINN become combine deep learning with the law of physics, and unlike the ordinary neural network, PINN do not rely on the data only. They learn also from the differential equation. And suppose we want to solve the heat equation. Instead of generating the million of training example, we simply provide a few observations, like the governing equation of the heat equation and the boundary condition. The neural network learn the solution while satisfying all that given equation, that model, the heat equation with the given boundary condition. Okay, so this significantly reduce the amount of loss of data, right? But in this case, only we are producing in the model only the governing equation along with the boundary condition. Okay, so another important advantage is physical consistency. This prediction automatically satisfies the governing equation because we are training on that governing equation. So this makes PINN extremely attractive for engineering, physics, chemistry, environmental science, and lots of topics. So today, PINN is considered one of the most promising research areas in scientific machine learning. So now let us understand why researchers are so excited for PINN. So as we are saying, first, PINN require less training data. Secondly, they manually naturally satisfy the physical law. And third, they solve differential equation. Fourth, they can solve both forward and inverse problems. Another advantage is that they are mesh free. So in this case, we don't have to do that thing. So unlike many traditional numerical method, PINN do not require mesh generation. This makes them attractive to completed geometries. So PINN are especially useful when the experiment data are limited, because we already discussed that the situation where the data are very limited. Okay, so but obviously, although the PINN are still developing, they have already um, demonstrated impressive performance in many scientific applications. Okay, so now we are looking for PINN architecture. This is very important. So the architecture of PINN is very similar to an ordinary neural network. So the input consists of space and time conditions, for example x, y, z and time t. So this input passes through several hidden layers. So each hidden layer performs mathematical calculation, and finally the network predicts the unknown physical quantity. Okay, for example, it may be temperature or pressures or velocity or displacement, etc. But there is no important difference. Okay, there is one important difference, and what is that? It is in an ordinary neural network, training depending on data, but in PINN, training also depend on the governing equation. So the neural networks must satisfy both, obviously. So this is an additional physical knowledge to make the prediction much more reliable. What is the core idea? The core idea is, I can say that normally the loss function compares the prediction with the observed data, and in PINN the losses are multiple parts, and these parts measure the data error. The second part measures the boundary condition error. The third part measures how well the governing equation is satisfied. And if the neural network violates the physical equation, the loss increases. Right? And the optimization algorithm automatically adjusts the network weights. Training continues until all three errors become very small. So this is how the physics become the part of the learning process. So instead of learning only from the observation, the network also learn from the scientific knowledge. So this is the key idea behind the physics informed neural network. Now, this is very important. Physics laws and the PD residual. So suppose a neural network predicts a solution. So how do we know whether this solution satisfies the governing equation? So we simply substitute the predicted solution on the differential equation. If the equation perfectly satisfied, then the result becomes 0. Obviously, we already know that how to check it out, that our solution in algebraic equation. Suppose we is finding the roots. If our roots are correct, then if we are putting the value of the root in that equation, then what happens? That it will satisfy the equation. So same thing, we can do this thing. And if the result, if it is not satisfied, the remaining error is called PD error. Okay, remaining error is called PD residual. So our objective is to minimize this PD residual, and during the training, the optimization algorithm continuously reduces the PD residual. And eventually, what happened? The predicted solution satisfied both experiment data and as well as the given governing equation. So you can think that of the PD residual as a teacher. Okay, so whenever the neural network makes a mistake, the residual tells it how to improve, and this makes the learning process much more physically meaningful. Now, automatic differentiation, AD. What is that? Now, PYN require many directives. For example, the heat equation consists first and second derivatives. The Navier-Stokes contain several special derivatives. Calculating these derivatives are accurately is essential, obviously. So instead of numerical approximation, what we can say that PINN use AD, that is automatic differentiation, and this automatic differentiation is neither symbolic differentiation nor numerical differentiation. It actually combines the advantages for both. So neural network automatically computes what I can say that exact derivatives using the chain rule from calculation. Right. So this process extremely accurate, and it is also computationally very, very efficient. So automatic differentiation is one of the key technology that makes PINN possible actually. So without this AD, the training PINN would be extremely difficult. So this actually the training workflow of PINN. And so this slide actually from the first, if we are saying that we define the governing equation, this is very clearly visible in this slide. So first the governing equations we have to define. Next we specify the initial and the boundary condition. Then we construct a neural network. Then the network predicts the unknown solution, and using automatic differentiation, and we calculate the required derivatives. Sorry. We calculate the required derivatives. So next we compute the data loss and boundary loss and physics loss, and all these losses are combined into one total loss. The optimization algorithm updates the network weights. Okay, so this process is repeated many times, and the neural network produces a solution that matches the data and satisfies the governing equation. So this completes the physics neural network, the framework of this thing. Okay, so notice something very important. What is that? The traditional deep learn only from data, deep learning learns from data, and traditional numerical methods solve only the equation. And what is PINN actually do? PINN successfully combine both approaches into one undefined framework. So this is why the many researchers believe that PINN represents one of the future direction of the scientific intelligence. We are considering here some of the examples heat transfer. For heat transfer occurs everywhere. So it happen in mobile phones also. So it happen in laptops, it happen batteries, power plants, etc., etc. So engineers often want to know the temperature changes with the time and position. So traditionally we solve this problem using heat equation, right, with the partial differential equation. We already know that thing. So usually numerical methods like what method we can use, the finite difference method, or we can use the finite element method to solve that heat equation, right? Now this method requires mesh generation, and that is very complex, right? So in PINN solve this problem. How? Instead of creating mesh generation, we build a neural network, and that inputs to the network are the space and time coordinates. For example, if we are considering x, y, and t, so the input or the output of the output will be the predicted temperature. So during training, the network learns from two sources. First, it uses available temperatures measurements, and secondly, satisfy the heat equation itself. So these are the two. And if the predicted temperature violates the heat equation, that is then what we can say that loss increases, the network automatically corrects its prediction. So eventually, if we are saying that the model predict the temperature distribution while the satisfying the laws of heat transfer. So this is why the PINN is called physics informed. Okay, physics informed. So they do not satisfy, they do not simply fit the data, right? They also obey the physics. Another example, we can say that fluid flow, which satisfy the Navier-Stokes equation. So in this case also, we are using the same thing. Okay, so I'm not go through the deep explanation of this one. This is very important: forward problem and backward inverse problem, not backward, the inverse problem. Okay, so in scientific computing, what happened that we usually solve two type of problems. One is a forward problem and second is inverse problem. Now, let us understand the difference. What is the difference? In forward problem, we already know the governing equation, the materials of the properties, the boundary conditions, and our object. What is our object? Is simply to calculate the solution. So this is the forward problem. Okay. Now, if you are considering one example, suppose we know the heat equation, the thermal conductivity or the initial temperature, then we can easily calculate the future temperature distribution. Okay, so this is a forward problem. Now consider another situation. Suppose we made a temperature, but we do not know the thermal conductivity. Can estimate this known parameter, unknown parameter? So this is called inverse problem. So this is very, very important nowadays. In real life situation, inverse problem is very, very important. Okay, so inverse problem are generally much more difficult. It is obvious. So fortunately, PINN can solve both forward and inverse type of problem. So this is one of the biggest advantage I can say. Okay, so they can simultaneously estimate unknown physical parameter while solving the governing equation. So this make problem useful in medical imaging. Or we can say that material science, environmental science, geophysics, etc. Okay. Now, the strength and challenges for PINN. So the first advantage I can say that data efficiency. PINN required much less training data than the traditional deep learning. We already discussed this thing. The second one is physical consistency because predictions satisfy the governing equation. Third one is flexibility. PINN can solve both forward and inverse problems. Another important advantage, I can say that mesh-free computation. So unlike many numerical methods, PINN do not require the mesh generation. So this make them useful for complicated geometries. So however, I can say that PINN also have several challenges. Training can be slow, or optimization is sometimes difficult, or what we can say that that selecting suitable neural network architecture requires our experience. For highly nonlinear problem, training may become unstable. Or another challenge is scaling. So very large three-dimensional problems, what we can say that remain computationally determining. Right? So therefore, our PINN are not replacing the traditional neural network. Instead, with the existing numerical techniques. So beyond PINN, what I can say that PINN are only the beginning. Actually, the scientific AI is evolving rapidly. Researchers are now developing many new approaches. For example, neural operations, Fourier neural operations, or graph neural network, or hybrid physics AI models, etc. Okay, so this method aim to solve larger and more complex scientific problem, right? So another exciting direction is digital twinning. So in this case, the digital twin is a virtual copy of the real physical system. For example, a digital twin of a wind turbine, a power plant, or a smart factory, I can say. Okay, so artificial intelligence continuously update the digital twin using real-time sensor data. These allow engineers to monitor the system health, the predict the failures, or I can say that optimize the performance. Okay, whereas the future scientific AI will combine physics, mathematics, machine learning, and high performance computing. Also the cloud computing. So the goal is faster, more accurate, and more reliable for scientific simulation. So we are near the end of our talk. This is the evolution of computing challenge. So actually, this slide summarizes our entire talk from the beginning to this part. So initially, computer follows fixed program. Everything depended on human writing algorithm, we already discussed. Next came machine learning. Instead of writing rules, machine learned from data. Then come deep learning. Neural network automatically learned features from raw data. And today we are entering a new stage, physics guided intelligence. So here the artificial intelligence system learn not only from data but also from the scientific knowledge, right? Computing is becoming more intelligence, and it is becoming more efficient also. So it is becoming more scientifically meaningful, we can say. So future AI will not replace mathematics. Instead, it will work together with mathematics and physics, right? So the future computing paradigm, I can say that the artificial intelligence will continue to grow. Physics-based modeling will remaining essential. The high-performance computing will provide computational power, and cloud computing will enable large-scale simulation. Then we can say that the quantum computing may solve problems that are impossible today, and or very difficult, or we can say, and scientific machine learning will combine all these technologies, right? So instead of choosing between AI or physics, mathematics, so the future system will integrate actually combinations of all these things. Okay, so this integrated approach will help solve many grand challenges. And this representing scientific AI expanding into many research areas. One important field is healthcare. AI is helping doctor diagnose the disease more accurately. Climate science is another major application. AI help to predict weather, study the climate change and monitor the natural disasters, right? And medical science also use AI to discover new materials. Drug discovery has become much faster using artificial intelligence. And space agencies use AI for satellite analysis and planetary um, exploration. Right. So smart cities also use AI to magnet traffic, energy, and pollution. Okay, so scientists are also combining AI with robotics, with Internet of Things, with computer computing, okay, quantum computing, right? So this emerging field shows that AI is becoming an essential tools across science and engineering. So for young researcher, this is an excellent time to enter this field, and many exciting research opportunities are available. So in conclusion, I can say that we started our journey with traditional computing. We saw that traditional computing simply followed the programmed instruction. Next, discuss machine learning. Machine learning learned from the data, pattern from the data, and then we explored deep learning. Natural neural networks are automatically learned features and transformed artificial intelligence. However, deep learning has important limitation. It required large data set, it may violate physical laws, and this motivates the development of physics guided intelligence. And we learn about physics informed neural network. PINN combine neural networks with different shell equation, and they required less data, as we are discussing earlier. So they produce physically consistent solution. And finally, we discuss the future of the scientific AI. The future is not about replacing physics or mathematics with AI. This is about the combining the strength of both. Right. So this combination will transform engineering, science, medicine, and industry. So artificial intelligence is changing the world, but the next generation of AI will not only learn from data, it is also understand the laws of nature. That is the feature computing. And thank you very much for your kind attention. I hope this session has provided a clear understanding of the evaluation of artificial intelligence from traditional computing to machine learning, to deep learning, to finally up to my talk up to physics informed neural network. I believe this area will play an important role in the future engineering, scientific computing, or the interdisciplinary research. So if you are working in mathematics, computer science, or electronics, I encourage you that to explore scientific machine learning and the physics informed neural network. So these areas offer many exciting research opportunities actually. So thank you once again to the organizer for giving me this opportunity to share my thoughts with you. Thank you very much.
Thank you, ma'am, for giving your valuable time to us. Now I will request our session chair to conclude the session.
Thank you, madam, for your enlightening presentation. I have some questions from the audiences regarding today's session. So the first question, since unsupervised learning discovers patterns without labels, how can we determine whether the discovered patterns represent genuine structure in the data rather than artifacts introduced by the algorithm itself?
May I see the question? Where is the question? Is it written in the
Yes,
chat
yes, yes.
box?
Yes, yes, yes. It is written in chat box.
I can't find out the question. Very large question actually.
Yes, madam.
Mm, this is not the question.
It was asked by the Samik Bhattacharya at 3:09 p.m.
Yes, I can find out the question that since the unsupervised learning discovers pattern and without labels, how can we determine whether the discovered patterns represents genuine structure in the data rather than the artifact introduced by the algorithm itself. I want to ask Shamik Bhattacharya, are you there?
Yes, madam, I'm here.
So your question is not clear to me. Can you please tell me that what do you exactly want to know?
I'm just asking that if say the algorithm is executing and the patterns are determined, so what kind of patterns are real or imagined, say hallucinated patterns? Can you?
Hallucinate? Huh? Yes.
Asking that. Not real, meaning not real patterns.
So you are asking that if hallucinated patterns it produced by this machine
Algorithms, yes.
learning or deep
Yes, yes.
learning.
Yes, yes.
So hallucinated patterns means actually it's totally depending on the given data set as we are discussing. As we know that if your data set is very good, then your result will be good, right? So whenever the whenever you got any pattern from the given data set, that is totally depending on the given data set, the quality of the given data set. So if if the quality of the given data set is good in nature, then it will produce not accurately, but you can work with that.
Okay, thank you, madam. Thank you.
Madam, and the next question is, why do PINN struggle with high dimensional problems?
High dimensional problems, actually this is the nowadays the given, obviously, because this is one of the limitations of the PINN problem, because we already know that sometimes the data having the high dimensional means that a lot of parameters exist in their data. So what happened that PINN we discussed earlier that that it works with the it's what not only the data but also with the given the differential equation with with the initial conditions or the boundary value condition. But when the high dimensional data are there, so in that case what happened, the number of parameters increase. Okay, so it is sometimes fetching difficulty to use all the parameters. If we are considering all the high dimensional means all the many more parameters are there. So combining all that parameter along with the given differential equation or the PDE with the along with the initial and the boundary value problem. So this will happen that parameter not work suitably with that the governing differential equation. So that is one of the drawback of that. That is why that physics informed neural network only not the final one, because after that lots of computing methods, quantum computings are also there. So this is one of the drawback.
And ma'am, the last question from one audience: difference between the deep learning and reinforcement learning.
Right. So in deep learning, we already discussed that what happened, that it requires large data as well as it requires labeled data. But in reinforcement learning, what happened, that I am already discussed in my session, but still in reinforcement learning, what happened, the program learns in step by step. So in first step, suppose the program, whenever we run the program, whatever the difficulties or errors are there, the program learn on that and redesigned the program by itself, by the computer, and try to less that error. Okay, so this is reinforcement learning. So it will learn in every step and correct the backend program.
Thank you, madam. On behalf of the organizers and all participants, I extend our sincere gratitude to you for this excellent session. With this, I formally conclude the session. Thank you all for your participation.
Thank you.